Hi everyone, so we're very happy to have Saad from Stanford. He's going to tell us about late-time correlation functions, bending universes in JT gravity.
Cool. Thanks everyone for inviting me here to talk. So yeah, I'm going to be talking about some work that I wrote up in a paper a few months ago, and then at the end maybe I'll say some things about future directions, things that I'm thinking about now related to this. Okay, so I'm going to start out with a bit of motivation. So the big motivating question behind this work is just a set of questions related to probes of the discrete spectrum of black holes in gravity, and the distinguishability of black hole microstates from outside the black hole. And so a classic question in this line of questions is due to Maldacena, who said, think about the eternal black hole, simplest black hole you can think of in ADS. And then take that state and perturb it with a simple operator. And you can think of that operation as just drop in a particle at time equals 0. So if we choose to do that by implementing this operator here with O, and then we measure the one-point function of O in this perturbed state, we'll find that the one-point function is not 0, even if the one-point function in the thermal field double state was 0. So physically, that can be like, we're measuring the one-point function of a field where we threw in one of those particles. Well, obviously, at short times, the one-point function is not 0 because we can measure that the particle is right there outside the horizon. But if you wait a little bit of time, the particle is more and more likely to have fallen into the black hole. The one-point function will decay. Now, semi-classically, this one-point function we expect to go to 0. It'll just decay forever. But if the black hole has a discrete spectrum, we do not expect this one-point function to decay forever. It'll have some interesting behavior at late times. So this one-point function is a nice physical question, but there's another related quantity which is also nice and physical, which is the two-point function of this field O in the thermal field double state. And we can think of this as being related to the one-point function by the small epsilon limit. So similarly, this decays for early times, and we can maybe think of that physically by thinking of this as a transition amplitude. We have an initial state which is O acting on the thermal field double. So we create a particle outside the horizon at time 0. And the final state is O at time t on the thermal field double. So there's a particle outside the horizon at time t. So this is the amplitude for a state with a particle outside the horizon to evolve into a state with a particle outside the horizon. And of course, this decays for the same reason, which is that the particle is more and more likely to go into the black hole instead of staying outside the horizon. So for early times, we have a pretty good idea of why this quantity behaves the way it does. This decays, and the decay is described by the quasi-normal modes of the black hole. But we can see that something interesting happens if we think that this black hole is a discrete spectrum. We can write out in this way by inserting complete sets of energy eigenstates. So we can take this formula on the bottom here, process it by taking the long time average. So here, we're going to assume there's no degeneracies in the energy spectrum. That's not important. That just adds little factors. So what we do is we integrate this over all time, divide by the time range, and we take the time range to infinity to get the infinite time average. Oh, there's a little bit gone at the bottom of this. Oh, that's OK. There we go. And so this long time average is not 0, but it is exponentially small in the entropy of the system. So a quick way to see that is we have a double sum over energies here. We have e to the s times e to the s terms in this sum. And the long time average restricts us to a single term, where we've set the two energies equal to each other. So we're summing over exponentially fewer things. So
what about the fact that the spectrum is discrete?
So the fact that the spectrum is discrete means that this the ratio of the time 0 one to the infinite time average is finite. So the ratio is.
No integral there.
Pardon me?
Because there's no integral over energies?
Yeah. So it's if you took the limit as the energy levels become the spacing goes to 0. Well, so you can actually think about it as the ratio is the spacing between energy levels. And we take that to 0, then the ratio goes to 0. So here's a rough picture of what we expect this thing to look like. So it decays for early times. Something mysterious happens. And then this red line is supposed to show this infinite time average. But around that, we actually expect it to fluctuate very erratically. So the details of these erratic fluctuations depend sensitively on the actual values of the energy eigenvalues and the matrix elements of the operator. So it's very, very fine-grained information to know the actual signal here, but there's a simple thing which is somewhat insensitive to the details. So this is a very coarse picture of what this function will look like. But already we can see that maybe there's something that's hard to see in gravity, which is this non-zero average value that seems like it's maybe calculable because it's not this crazy erratic thing. So quantities like that seem like a good set of targets for trying to understand some aspect of this discreteness of the black hole entropy.
So right now your argument doesn't care it's a black hole, right? It'll apply to any
Yeah.
system.
So basically what I'm going to do for the first chunk of this talk is I'm going to say if you have a chaotic system with a discrete spectrum, what do we expect generally? There's some universal behavior. Then I'm going to say in a specific model of gravity, we're going to go calculate these things. So we have this erratic signal, and we considered this time average of this thing and found something simple. If we have an ensemble of systems, each one has a discrete spectrum, but we have an ensemble of these systems. An example of this would be SYK. We can consider a slightly simpler problem, which is where we calculate this correlation function and then we average over the ensemble. So for each member of this ensemble, the correlation function will not decay. So what that tells us is that the average will not decay. But we expect that probably the average over the ensemble will smooth out these erratic features and leave something like the time average. And more precisely, there's some reason to think that the average of the ensemble will look a lot like what you'd get if you took this signal and didn't do the infinite time average, but averaged over small enough time windows to average out the erratic stuff. So that here you'd find a value that's the average over these fluctuations, and there, and there, and there. And that would approximate the quantity you'd get by averaging over an ensemble.
So
Yeah.
how big would you expect the ensemble has to be? How many different theories do you need before you have effective averaging?
That's a really good question. It's really not clear. In the model that I'm going to talk about, you have a huge ensemble. In SYK, your ensemble is much smaller, but you still have many members of the ensemble. You have, if there's n fermions in the SYK model, you have like n to the fourth members of the ensemble. There's some preliminary numerics that show you can take the SYK model and get nice, smooth average things by averaging over just a few members of the ensemble. You take one parameter, there's a huge space of couplings in the SYK model, but if you take a simple one parameter family of them and integrate over that, then you get very nice average looking things.
Oh, but a smooth one parameter.
Yeah, so it's still infinitely many, but you average over it. And then you can imagine just cutting that up into little bits, and you expect by discretizing that one parameter family.
I'm wondering if this was a standard thing. I mean, if I wanted to have effective averaging with n theories in a situation like this, where you have a fluctuation that's upward of the average, I guess.
Yeah.
Presumably, there's some formula of what n has to be at least, right?
Well, it'll depend on the details of like something like the autocorrelation time, stuff like that. It'll depend on some of the details. It's really hard to make a precise estimate of how much averaging you need to do. But that is a really good question that I think we've been thinking about for some time. And then also maybe I'll just emphasize here that a lot of the averaging that reveals features like the things I'm going to talk about, you don't need to consider an ensemble. It's convenient to have an ensemble. But you can consider things like this time window averaging. And there's still a question, which is how long do the time windows you have to average over, how long do they have to be? That'll depend on the system. And there you can make a little bit of some precise predictions. But the point is, I guess, that the ensemble isn't required for talking about the things I'm going to talk about, but it is very convenient. And in the end, we're going to want to think about something where there's no averaging at all anyway. So, OK, so I guess I want to end this slide with this question here. There's this erratic behavior, and we've seen that there's a simple average thing underneath this erratic behavior. But then there's all sorts of other quantities you can ask about this erratic function. You can ask about statistics, not just the average. You can ask about moments and stuff like that. And to what extent are all these various measures of this function visible in gravity is a question that we're going to try to think about.
You can ask a quick question. So
Yeah.
how big are the deviations from the average for these sort of things that you're talking about?
So the things I'm going to talk about in this talk, the deviations are large, in fact. So we're gonna get to that, but yeah. So we're gonna find a function where the fluctuations are of order the size of the signal. So the average is a very bad approximation of the actual function, which is, I think, makes the question of what happens when you don't average a lot more interesting in this case. And we'll talk about it a little bit more at the end, though. So for now, I'm just gonna go on and talk about a specific example which we'll try to study these questions in, which is JT gravity. So it's a nice two-dimensional theory of dilaton gravity, and it's got this Euclidean action. So this action has three different parts. First, we have this topological term. So the action is proportional to the Euler character, but the constant of proportionality, S0, we want to think of as large. In the context of the SYK model, S0 is proportional to the number of fermions. So we want to take it large so we have a nice topological expansion. We have this other term in the action here where we can see that the dilaton phi is multiplying r plus 2. So if you integrate out phi first, then you have a delta function setting r plus 2 equals 0. So this is saying that we only integrate over constant negative curvature manifolds. In 2 dimensions, the scalar curvature being minus 2 tells you that the whole Riemann curvature is constant. So we additionally have this last term, which is an action for the boundary. It's not going to play a huge role in this, in what I'm going to talk about, so maybe I'm not going to mention it really. So this is the Euclidean action, but if you try to quantize this theory on a line with asymptotically ADS boundary conditions, there's 1 degree of freedom, which is the whole length of this line. Really, if you have 2 asymptotically ADS boundaries, the length is infinite, but you can talk about a renormalized length, and that's the single degree of freedom. So this theory, JT gravity, has an interesting property, which is that it's described by an ensemble average of systems. So with Stephen Schenker and Douglas Stanford, we found that if you try to calculate something like partition functions in JT gravity, here z of beta 1 through beta n means the Euclidean path integral with asymptotically ADS boundaries with renormalized lengths beta 1 through beta n. You try to calculate that by summing over all geometries and all topologies. You find that this quantity is not just the product of a bunch of partition functions like you might expect. It's actually the product of a bunch of partition functions for a fixed Hamiltonian h, with then you average over h, where h is drawn from some ensemble described by this p of h. And I'm going to tell you the details. But the moral here is that JT gravity is an ensemble of systems like SYK. So if I want to calculate a quantity in JT gravity, say I want to calculate this partition function, this correlation function in JT gravity, I'm not going to expect an answer which looks like that formula I had written for a set of discrete energy eigenvalues. Instead, I'm going to expect a formula that looks like what I'd get if I took that formula and then averaged over those parameters like the eigenvalues and eigenvectors drawn from some ensemble. So I just have a picture here of a candidate geometry that makes this seem a little bit more sensible. If you have these geometries which connect the different asymptotic boundaries, that seems to make it look like this partition function, or this set of partition functions, is not going to factorize. So that's something that's consistent with this averaging that I'm talking about. And you'll have to trust me based on earlier work that you in fact do get such a exact correspondence like this. So with this motivation that JT gravity is described by an ensemble of Hamiltonians, we're gonna make some predictions, some precise predictions for the way this two-point function is going to behave in this theory. So the predictions are going to be based on this theory being chaotic. So additionally, we're going to, because we want to talk about our two-point function, we're going to put some matter in the JT gravity theory. We're going to put a free scalar field. Interactions won't change the story much. And then we're just going to assume that this theory also behaves like an ensemble average. Later we'll find that it does. But for now we're just going to make some predictions, and then we're going to try to see what we get when we actually calculate things. So we can talk about a lot of two-point functions. We can talk about the left-left, the right-right. But we're going to talk about the left-right one in particular, because it's a little simpler to calculate. Later we'll be able to see how the other ones behave. But this two-point function we can think about in two different ways. The first one is like this transition amplitude I talked about earlier. You start with a state where there's a particle here. You end with a state where there's a particle here. The second way, which we get by shifting the times using the symmetry of this state, is like looking at the expectation value of O left of t over 2, O right of t over 2, in the state that's the thermal field double. So this expectation value picture is actually going to be a little bit. It's nicer to keep that in mind when doing the actual calculation. So I'm going to stick with trying to think about that, and then we'll go back to this transition amplitude picture later.
Can I ask a
Yeah.
question about, sorry, this was something you said on the previous slide, but the fact that the correlation function doesn't factorize, you said is similar to the, or sort of somehow equivalent to the fact that we're considering an ensemble average?
Yeah, so it's not equivalent. So the fact that it factorizes is consistent.
In
So
what sense are they related?
if you have, if you're doing an ensemble average of partition functions, then you expect your partition function to not factorize, but not the other way. Not the other way. Yeah.
Yeah, because that happens in QFT.
Exactly. Yeah.
Okay.
So let's see. Yeah, this geometry here that I showed you is just it's not. This isn't showing you that you have an ensemble average, but it's showing that it doesn't factorize, which is one of the weirder consequences of the average. So now we're going to take this expectation of chaos in gravity. Yeah.
Just a question of what is the thing that is not the case? So what am I?
If you go in gravity and you calculate what you think are a set of partition functions, but you include these geometries that connect the different asymptotic boundaries so that it's not factorizing, that doesn't necessarily tell you that the answer you get looks like a nice ensemble average over partition functions. Because you could find that you get a formula that looks like what I had here with this P of H. But then P of H can go negative, so it's not a real average over some probability distribution. So including geometries that look like this, which cause this set of partition functions to not factorize.
But you could still exclude the possibility that there is a unique theory.
Yeah.
It just could have been even worse.
Yeah, it could have been even worse. Could have been even worse. Yeah.
That's what
Yeah. So one of the things we're going to input for our prediction that we'll later try to actually find as an output of the theory is that the matrix elements of this operator O that we're considering obey the eigenstate thermalization hypothesis. So we don't really have to put in the whole machinery of the eigenstate thermalization hypothesis because the two-point function only cares about the modulus squared of these matrix elements. It doesn't depend on the phases. So ETH tells us that these modulus squared of these matrix elements should behave something like a smooth function of the two energies. And the function should be exponentially small in the entropy. It's not very important for us. The random phases, I'll just make a side comment. If you consider things that are higher point correlation functions, they'll be sensitive to the phases, and you can also do some calculations and find some interesting consequences of the behavior of these phases in the late time behavior of correlation functions. And then JT gravity seems to match the predictions of ETH. That I probably won't talk about anymore. So now we go back to this formula for G. I've replaced the matrix elements with this smooth function f at the end there. And now I've written the sum over energies as an integral over energies weighted by the density of states. The density of states is like a sum of delta functions if you have a single system. But we're averaging over systems. And here we're averaging over the product of two densities. So for early times, it turns out to be a very good approximation to take this average of a product of densities and think about the factorized average. This is because when you have large numbers of degrees of freedom, the the fluctuations of the average density around its mean are very small compared to the actual density itself. So we have this factorized contribution for the two densities. If you plug that in there and you assume that the densities are smooth, you expect that this function decays because you're essentially Fourier transforming a smooth function. However, for late times, when t is very big, this integral over energies is going to be dominated by the two energies being very close to each other. So there's some important corrections to this factorized form of the densities. And so what are the details of these corrections? Well, in JT gravity, we can calculate these things and find agreement with some very general expectations based on chaos. So the general expectations based on chaos are that eigenvalues repel. So what is this question, the average of rho of E prime? That's saying, given an energy at E, what's the probability of having one at E prime? Well, there's a picture here on the bottom which is not very big. I'm going to draw it on the board here a little bit bigger. Is this visible to everyone? Mostly it's going to be this part that's important. Actually, you know what? I'm going to forget about it. I'm just going to move this up. Can everyone see this pretty clearly? Yeah, it's big enough, I suppose. So this, you can't really see here. This is supposed to be this pair of densities, and this is the differences in energies. So in a chaotic system, eigenvalues like to repel, much like the eigenvalues of a random matrix. So the likelihood of having two eigenvalues nearby is small, and there's a delta function peak at the difference in energies being 0. But away from this 0, there's a little peak here at the average level spacing, so which is exponentially small in the entropy.
Are you going to explain how you calculate it?
Yeah, well, the way you calculate it is by calculating all these partition functions. You calculate a product of two partition functions in JT gravity, which is this average thing. And then you just Laplace transform that to get the density correlation. So this thing here has got a little peak at one average level spacing, and then another peak that's a little bit shallower at the next level spacing. So the eigenvalues like to be somewhat evenly spaced, and they don't like to be too close to each other. So this sort of function here is expected to be, like in the precise details of this function, in fact, are expected to be universal for chaotic systems. So we can calculate it specifically in JT gravity, but we expect this to be pretty general. And so that's important for thinking about how anything I'm going to say is going to generalize to more general black holes. Yeah, you.
Sorry, do you have direct access to the spectrum, or you have to compute this 2-point?
We can calculate the average spectrum, but then it's going to be the average that we calculate. So some of these features are a little bit more like going to 0 here is a nice clean smoking gun of discreteness for average things. Is considered a lot in the quantum chaos literature. For the average density, you'd find that there's ripples in it that are similar signs of the discreteness, but this is, yeah. This is going to be more directly relevant for the 2-point function, which we're considering. So if you take this formula here for this density correlation and plug it into our formula for the 2-point function, you find that it should behave like this. There's an initial decaying region, which I talked about. This is the semi-classical thing. But then in addition to a late time exponentially small value, we find this interesting linearly growing thing. So here this is a log-log plot. So this difference here, this is an exponentially small difference, and then here it's like e to the minus 2s small. So we find in addition to this late time average, this thing we call the ramp, and the plateau, we're going to, maybe I'll say like 2 words about it at the end. It's not that different than the ramp in its gravitational origin. So we're going to focus on trying to understand the ramp in this talk.
So in slope, is that power law decay? Or is this
It starts exponential, then it goes power law.
Is that universal?
I don't think so. It's actually, it changes if you try to consider not this fixed temperature correlation function, but a fixed energy. I think it's exponential then.
It's always exponential.
I'm not really sure. It's It's a little bit harder to calculate at really late times, and I haven't done the calculation. Yeah. But for fixed temperature, yeah, it's power law. The semi-classical part is like power law forever.
The existence of the ramp is also universal.
The existence of the ramp is expected to be universal, and the ramp comes from, if you approximate that figure I had on the previous slide, by a smoother thing that doesn't have these rapid oscillations. And that we expect to be very universal in chaotic systems. So this ramp is not a funny feature of the specific JT gravity theory that we're considering. It's an output of a general expectation from quantum chaos. So if we take that formula for the two-point function which I had and delete the matrix elements, you get this thing called the spectral form factor. It behaves similarly. It has a slope, as a ramp, and as a plateau. So instead of having the matrix elements, it's got this density thing that I was talking about. And because it has a similar shape, it seems like maybe learning about this thing will tell us about the two-point function. In fact, the gravitational behavior underlying their behavior is pretty similar, so this is a good idea. But we're going to talk about this as a sort of warm-up for the two-point function. So I've written this quantity as z of beta plus it modulus squared, which you can see just by processing the right-hand side. You take a partition function, two partition functions, analytically continue them, and then you average. So how does this thing behave? And in particular, how does the initial slope and ramp behave? So this quantity here, the z of beta plus it, you can actually see, if you work it out, see that this is like the probability amplitude for the thermal field double state to be time evolved and then end up in the thermal field double state. So people call this the return probability of the thermal field double state. So in gravity, the thermal field double state is dual to the Hartle-Hawking state. In JT gravity, the Hartle-Hawking state is pretty simple because we can talk about its wave function in the length basis, because length is the only degree of freedom. So we can calculate the Hartle-Hawking wave function in the length basis by integrating over all geometries where we have this asymptotic boundary of length beta over 2 and some geodesic boundary of length L. So z of beta plus it is not the return. We take the modulus squared to get the probability. But this thing itself is just the return amplitude of the Hartle-Hawking state. So we can get it by, one, calculating the partition function with a boundary of length beta, and then continuing it. So we'd have an integral over some complex geometries with a topology of a disk. And that's not very, it's a little bit confusing to think about those. You could equivalently think about it in a way which corresponds more closely to this way of writing the quantity, where you take the Hartle-Hawking state, evolve it for some time t over 2, and then take the overlap with the Hartle-Hawking state again. So these are two ways of doing the same. These are two ways of expressing the same quantity. These are just, if you take the path integral for gravity, you do an integral over geometries with some boundary conditions specified. And the boundary condition is the boundary metric. Now this quantity is only sensitive to the total length of the boundary, not the actual details of the boundary metric. So we can change the boundary metric corresponding to either of these two pictures, and it gives the same result. So because of the topological term in the JT action, this piece here comes with a factor of e to the s, because this has Euler character 1.
So in this picture, are you specifying L and L prime also? Or
So I'd be integrating over those.
Yeah.
So here it's like I start with the wave function and then I take a propagator. Yeah. We can look at the function itself when it's just time evolved. So we can look at it on the L basis. And thinking about how this behaves will teach us about the relevant behavior in gravity. So the wave function for time equals 0 is peaked around small l. So this is L, you can roughly think of as the size of the Einstein-Rosen bridge between the two asymptotic boundaries. As you evolve this geometry, the length of the Einstein-Rosen bridge grows, and it grows about linearly in t. So this wave function becomes peaked at L of order t. So this has the immediate consequence that the overlap with the initial Hartle-Hawking state decays. The initial Hartle-Hawking state is peaked at small l. The later time Hartle-Hawking state is peaked at larger L, and as you increase the time, the peak in L moves further away, and then their overlap decreases. So if we want to see a non-decaying contribution to this return amplitude, we have to understand some physics that will cause the length of the Einstein-Rosen bridge to be short again, so that it has a non-trivial overlap with the Hartle-Hawking state. So what kind of thing, what might we expect, causes the length of the Einstein-Rosen bridge to shorten? Well, one way to do that is to let the space emit a closed baby universe. So if we want to calculate the amplitude for the Hartle-Hawking state to evolve into a space where there's an asymptotically ADS region, but also a closed baby universe of size b, we do an integral over geometries like this. So here we have a geodesic boundary of length L representing the time slice of the asymptotically ADS region. Here we have a circular geodesic boundary of length b telling us about the state of the closed baby universe. Now I'm not going to tell you really about the details of how you calculate this thing. Really this is, here we can choose to do this integral by integrating over different contours of metrics. One nice choice is to do them over mixed Lorentzian and Euclidean geometries. Maybe I'll have a quick slide about that in a moment, actually. But in either case, this geometry has Euler character equals 0. So it's actually exponentially suppressed relative to the leading order disk topology. So you can find that if you calculate this thing, this wave function has non-decaying support at L back to of order 1, so a short Einstein-Rosen bridge, but where the baby universe has size of order t. So roughly what's happening is that the Einstein-Rosen bridge likes to grow to size of order t, but if you emit a baby universe, it can carry away all the length with it. So you can think about it as you have this Einstein-Rosen bridge as becoming a very, very, very long thing, and then it pinches off into a closed baby universe. And you take the parts at the end that were at the horizon and glue them back together. And then you have a state which looks like the initial state. Yeah, here's a little bit of detail. This actually may be worth talking about because it's becoming more important in some more recent discussions. When you're thinking about doing integrals over geometries like this, turns out there's no non-singular Lorentzian manifolds with this topology. But that's okay. These baby universes are like Instanton processes. We often think about describing those via some Euclidean path integral. And so we can describe something like this by having a normal Lorentzian evolution, and then we have a Euclidean tunneling part glued onto it. Here I've chosen a time slice at which to have this tunneling process happen, but the answer is independent of the time slice. It's like a gauge choice. So what you don't do is integrate over the time slice at which this occurs. You can pick one time slice, and that'll give you the full answer. So this gauge choice of choosing different time slicings is going to come up a little bit more, and then at the end is, this gauge choice of choosing different time slicings leads to a lot of interesting stuff. So now back to the spectral form factor. We had 2 copies of this transition amplitude to get the probability. So what's happening is this one's going forward in time, this one was continued backwards in time. So this one, the Einstein-Rosen bridge grows and then shortens. This one grows and then shortens as they trade this baby universe. The baby universe has a size of order t. And then there's t ways to twist this baby universe before gluing it back to the other one. Turns out that makes the quantity grow linearly with t, because the measure for this twist is proportional to the size of the baby universe. This has the topology of a cylinder, so it gives an exponentially smaller contribution than a decaying thing in size, but it grows instead of decaying. So it eventually dominates over the semi-classical decaying part.
Why does the number of ways rotate it?
So one way of doing this integral is by, you can think about there's a modulus here in the integral. They're constant negative curvature geometries. The integral is pretty simple, so you can nail it down pretty easily. And you can think about the integral over these geometries as including an integral over the angle here. And if you just work it out, you find that the measure is like, if the size of that circle is b, the measure is like b dB. So it's just, if the circle is larger, there's more volume to that integral. And then B turns out to be of order t, which you can think of as causing this linear growth. So this effect of shortening the Einstein-Rosen bridge by emitting a baby universe, we can use this to describe the ramp in this two-point function. So again, we're going to look at the early time behavior as a warm-up to get ourselves oriented. How do we do the calculation of the two-point function in gravity? Well, so we have two operators O and O, and we start by calculating the Euclidean. Well, one way to do it is by starting to calculate the Euclidean correlator and then continuing it. Later, we're going to see a little bit more of a direct way to calculate it in Lorentzian signature, but this is easier to get ourselves started up with. So here you have some boundary length beta minus tau, and here's some boundary length tau. And you integrate over all geometries. In this case, the disk is constant negative curvature, but you can change the shape of the boundary. So you integrate over all the shapes of the boundary weighted by the matter correlator on this geometry. So the matter correlator on this disk geometry is very simple. It's just e to the minus delta L, where L is the geodesic length between the two operators, and delta is the scaling dimension, simply related to the mass. So what we do is we integrate over all these geometries weighted by this function, the geodesic length between the two. So you can do this integral in a simple way by integrating up to a slice of fixed L, and then also integrating up to a slice of fixed L. That just means integrating over all the boundary behavior here and here. And then weighting those two pieces by e to the minus delta L, and then integrating over L with the correct measure. The correct measure you can just derive. So this is done by Zhenbin Yang in a paper of his. And he was able to calculate these things exactly and find a nice answer, which, as we might expect, decays for early times. So what is the physics behind that? Well, we take this thing and we analytically continue. So when we take these disk things and analytically continue them, we get time-evolved Hartle-Hawking states. We can see that each of these is a Hartle-Hawking state. And if you continue its temperature, you get a time-evolved version of it. So we have Hartle-Hawking state, time-evolved, Hartle-Hawking state, time-evolved, and then we measure the geodesic length between the two boundaries. So that's just looking at the expectation value of e to the minus delta L in this Hartle-Hawking state evolved for time t. The peak of the wave function is supported at larger and larger L as time increases, and so e to the minus delta L decreases. So we find a decaying piece of the correlation function. So again, what can we do to cause this thing to stop decaying? We can stop the Einstein-Rosen bridge from growing.
So why do we always ramping?
Oh, this is the whole section. This is not the ramp yet. Yeah.
Sorry, Phil, just in the picture, one of them is supposed to grow, the other one not, right?
Oh, no, these are both time evolved. So what I've done on the previous...
Then why does delta L get larger?
Delta L, so L is... So what I'm doing is, look, this is a state. And now here's like the density matrix.
Yeah.
So I'm looking at the expectation value of e to the minus delta L in this density matrix. So we've got two copies of the state.
There's L on both of these. So
Delta is the dimension.
Delta's just a
Oh, yeah, sorry. Yeah, it's like for large mass, delta is just mass. Think of it like that.
Oh, I see.
Yeah.
That's the dimension of the operator.
Yeah, I should have emphasized that more. Delta is like, it's related by that square root formula to the mass. So if we have a situation that's similar to this, but we're having a baby universe be emitted, we can imagine baby universe being traded between these two copies. That tells us to look at a geometry that's got the topology of a handle and a disk. So now we've got to do the same calculation, but on this geometry. And it's a little bit more complicated. Well, it's a lot more complicated. The reason is that we've got all these different geodesics. Here's this black geodesic goes around the handle. It's not important. This purple geodesic goes through the handle. So you can think of like if this is the length increases, and this baby universe takes away the length, this slice might have small length. What about this green geodesic which goes through the handle? Well, it's actually very similar to the purple geodesic by choosing a different slicing. So really the purple and green geodesics, we can choose a slicing here. If we cut along green, we find that there's this handle that it doesn't intersect. And we think about the handle as the baby universe. It's not obvious from this picture, but if you cut along the green thing, you get a similar geometry where there's a handle that you haven't intersected. and then we think of that as a Babe universe. So that would be something like a circle which goes along here and doesn't intersect the green thing. There's infinitely many circular geodesics on this handle which are distinct. Each one of those we can think about a Babe universe, and we can think about doing a time slice that doesn't intersect it. So exactly, yeah. These are all just like modular images of each other. So we have to sum over all these geodesics on this geometry. Well, I think let me scroll down on this thing here. Yeah, just quick comment. The matter correlator on this geometry, because this thing is a quotient of the hyperbolic disk, it's a sum over images of the correlators on the disk. That make things technically easier because the formula for the matter correlator is just a simple exponential like before. Now we're just summing over geodesics. So we can think about the integral by picking a geodesic, doing the integral over geometries for that geodesic, and then doing that for each geodesic. And that's a little bit complicated for this reason. So say we pick the purple geodesic. We can pull the same trick that we did earlier, cut along this geodesic, integrate over geometries for fixed geodesic length, and then weight that quantity by e to the minus delta L, and then integrate over L. This should be Li, sorry. So the trouble here is if we do this cut, then we have an integral like this over geometries of this form, and we need to integrate over the size b here. This integral looks similar to the one we did before with this cylindrical geometry where b is of order t. However, we're not free to integrate over b from 0 to infinity. And the reason is, if we increase the size of b, the reason is that there's infinitely many circles on this geometry. So trying to classify this geometry by the size of that circle is not unique. If I try to integrate over b from 0 to infinity, I'd be overcounting like crazy because there's infinitely many other circular geodesics that can take the same sizes. And describing the geometry in terms of one geodesic, you need to pick some fundamental domain to integrate over. So it's hard to integrate over geometries like these, but it's actually simple to fix this problem because it turns out if you sum over all the geodesics, each gives the thing like this, but with b integrated over some fundamental domain. By summing over all the geodesics, you can trade that to a sum over fundamental domains, then the integral becomes simple. So that's a little bit of a technical thing, but I think the reason I want to mention it is the Euclidean path integral is giving this funny way to calculate this quantity where we have this non-unique, infinitely many number of choices of time slices, but the answer we get is simply described by choosing one time slice. So I think it's sort of interesting that the answer that we arrive at, where we freely integrate over geometries like this, but we've chosen one representative time slice, it's a simpler way to get the answer, but we got it from some more complicated thing. It makes me think there's another way to do the calculation in which you arrive at this through less of a convoluted path. So we can do the same thing that we did for the decaying contribution, take this Euclidean piece, continue it, continue it so that we get something like this spectral form factor. B turns out to be of size t, and we get a factor of t from the rotation. And then one thing that I should mention is that to really get our prediction on the nodes that we had from our expectations from unitarity and discrete spectrums and chaos, whatever, this thing needs to predict the right matrix elements. The matrix elements have to match with what you'd get from the decaying contribution, and that turns out to be true.
This round being linear in T, I think it's a feature of 0 plus 1 dimension.
Pardon me?
It's a feature of 0 plus 1 dimension.
No, so what you'd have in higher dimensions is you'd have like a sphere tacked onto here that's of sort of constant size, and you don't twist along that sphere. So, yeah, so you can think about this as the Lorentzian picture is we've emitted a Babe universe. Here it has a topology of a circle. In higher dimensions it would be the topology of a circle times a sphere. And in higher dimensions, this circle can be very, very big. The sphere stays of constant size. So in higher dimensions, the largeness of the Babe universe doesn't come from this transverse sphere. It comes from this one circle that's picked out as special. But maybe I'll say a little bit more about what we expect to happen in higher dimensions at the end. because I'm almost done. So the final thing I'm going to do is I'm going to tell you two different, more physical pictures of what's going on for this correlator. The reason I can have two different pictures is related to this non-uniqueness of time slicing this geometry. So there's one picture which is a more obvious output of the calculation that we did. It's very similar to the thing we had for the decaying thing, where you have a Hartle-Eigenstate, we evolve for some time t, but it can emit a baby universe so that the Einstein-Rosen bridge is short. And then we look at the expectation value of e to the minus delta L in that density matrix here. So here by looking at the density matrix on this asymptotically ADS part, we trace over the state of the baby universes. That just glues these baby universes together and creates a handle. So this is, you might say, we get an answer that looks like the expectation value of in a density matrix, not in a pure state. That's a consequence of the averaging. The average of a pure density matrix is a mixed density matrix. So here, the fact that these things are glued together makes this density matrix that's not pure. We can also think about, I'm just repeating what I've said before. So here, this is also, I think, maybe a more interesting way to think about it. We can think about this two-point function as a transition amplitude as well. The way to think about that is you let this baby universe, you choose a slicing such that the baby universe slice has the particle going through it. So what's going on here is I started with the Hartle-Eigenstate, I create a particle near the boundary. And then it can get sucked into the baby universe. And then I wait a long time t, and then I try to measure that particle later, and it can be re-emitted into the parent space, and then I can measure it. And so it hasn't fallen into the black hole, just got sucked into a baby universe, and then came back when I wanted to measure it. However, due to this gauge choice of time slicing, I could have chosen a different time slice for when this baby universe was emitted. I could have waited for the particle to go into the black hole. So I create the particle, wait time like 10 million years for it to go into the black hole. It's well inside the black hole. Then it gets absorbed by the baby universe, gets put out, and then comes back when I try to measure it outside the black hole. So depending on our choices of time slicing, two different things happen. One, it gets absorbed out near the boundary and then comes out, or another one is that it gets absorbed while it's inside the horizon and then comes out. And the answer is independent of this choice of time slicing. So just a quick comment about the Plateau. If you take this picture that I had for the ramp, and instead of making these two baby universes the same so that we sort of glue them together and make a handle, you let them be different. A certain way of doing that gives you the Plateau. You have to do something like using the replica trick to calculate this. And one of the ways to interpret what happens is that you have a correction to the inner product of baby universes. So here, if I thought about tracing out over the states of the baby universe, if I assume that baby universe states were orthogonal for different sizes, then I simply, tracing out over these guys, simply just glues them together. But if different baby universe states are not orthogonal, then tracing out of them is a little bit more complicated, and I have to include these extra corrections. So I'm going to end with some open questions. One simple generalization of JT gravity involves putting it on non-orientable surfaces or putting JT supergravity. And a lot of this was studied by Douglas Stanford and Edward Witten. It'd be interesting to see, so those theories are dual to different random matrix ensembles with slightly different behavior. Instead of having a simple ramp, you can have some curved thing, and it's universal up to some discrete symmetry class. It'd be interesting to see how that works out in that context. Maybe more interestingly is higher dimensional generalizations. So this ramp thing, the linear growth, is based on quantum chaos, independent of dimensionality. We expect for any quantum chaos system, the nearby eigenvalue statistics are pretty similar. So we expect this linear growth. What exactly happens in higher dimensional theories?
Are you saying that only thing it grows with t is
Yeah.
this one direction?
Yeah, exactly. Yeah.
And then it's partition and then volume.
Exactly, yeah. That's the picture I want to have. And then, but however, so there's an interesting difference in higher dimensions. And to see that, we can think about JT gravity as maybe coming from a dimensional reduction of some near-extremal black hole. So if you have a 4-dimensional near-extremal black hole, then you've got some near-horizon region that looks like ADS2 times S2. And the sphere, the transverse sphere, doesn't change much with size along this ADS2 region. So in higher dimensions, these amplitudes to emit and absorb baby universes depends on the area of this transverse sphere, but it's basically constant along this ADS2 region. So in JT gravity, there's no suppression for these baby universes to go out near the asymptotic boundary. That's related to this fact that the higher dimensional sphere doesn't change in size. But once you get away from this near horizon region, the transverse sphere starts to grow rapidly in size. That would cause a suppressed, that would cause the action to have a baby universe be emitted or absorbed from there to grow. So you don't expect these baby universe effects, we expect them to be suppressed outside of this near horizon region for near extremal black holes. And for more general black holes, we expect probably these effects are pretty confined to the near horizon region. So we've seen that these baby universes can take something from inside the black hole and put it outside. But probably it can't put it so far outside. It will just put it right outside the horizon. Maybe some of the most interesting questions are to try to understand what these things tell us about more interesting quantities about black holes. The black hole S matrix is probably the most interesting quantity. What does this tell us? So the 2-point function, S matrices, in ADS, their analog is like the set of transition amplitudes, or correlation functions. We've only looked at a very simple correlation function, but we can think about it as one of the most primitive transition amplitudes. So it seems like there's a picture for how this stuff might generalize to how they'd affect more complicated transition amplitudes. You have things inside the black hole, they can get outside, but the details will be much more complicated. But just in principle, this is telling us something that there's some new effects that we'd expect give interesting non-decaying behaviors in more general transition amplitudes. But to understand this, it's crucial to understand how to calculate these amplitudes for a specific quantum system, not an ensemble average. So the thing I found with this linear growth in this plateau, that gives you the really wrong answer for a specific system. The fluctuations are so large, it doesn't look anything like this ramp in the plateau until you average. However, if you try to do the gravity calculation to calculate statistics, these effects know all about the statistics of the signal. So even though it doesn't give you a good answer for a single shot of the system, it knows a lot about how it should behave in general. And then there's some recent hints about how we can probably modify the gravity calculation to calculate something for a single system. I'm not sure how much time I have left.
Can you say more about those hints?
These hints, yeah. So I have a couple. So let's see. Yeah. So.
I mean, in particular, it seems like everything that you talked about before could be regarded as a calculation of certain quantities.
Yes, like what goes wrong? Yeah, if you thought you were calculating something for a single system. I would say there's some extra stuff you have to include. So what is the sort of stuff I imagine is the extra stuff that fixes everything? Well, this is taken as a hint from the quantum chaos community, especially work done by Barry, where to calculate something like one of these analytically continued partition functions, you use what's called the Gutzwiller trace formula. And this is nice if you have sort of a particle in a funny potential. You can write this quantity as a sum over periodic orbits. And these orbits are labeled by A. And so if you calculate the spectral form factor, you have a double sum over orbits. But these ZAs for large times are have crazy phases. And they depend sensitively on the details of the system. They depend sensitively on the time. And so if you do any sort of averaging, these phases get averaged to 0. But then if you take this double sum, when you calculate the spectral form factor, and you try to average that, the phases cancel out if you consider just the diagonal components of the sum. And if you,
Like Z star.
yeah, Z and Z star. Sorry, there should be a star here. Yeah. This diagonal component of this double sum leads directly to this linear growth. So a gravity cartoon of this, which is actually, there's some recent work, I keep getting shocked by my computer. There's some recent work on some stuff called eigenbranes in JT gravity, which really provides a nice concrete partially average realization of this, where you have something like a double sum. Oh, and this double sum is over wave functions of baby universes. So instead of having only just baby universes that are traded, so no final or initial baby universe states, you include some final or initial baby universe states. And they're sort of you have baby universes emitted in like random states, basically. The random states have the detailed knowledge about the energy eigenvalues of the system. And there's if you take the diagonal part of this sum, you just sum over the two baby universe states being the same. That's like inserting a complete set of energy, a complete set of states there, and that just glues them together. So we can see how this cylinder part, which we saw, is included in this. But there's additionally there's these off-diagonal terms that are also added. So people have been arguing a bit about semantics here, I think, but you can think about it in two ways. One is that there's a double sum, and the things what we've seen are like the restrictions to the diagonal part of a double sum. Or you can think about it as we include the cylinder, but we add the off-diagonal terms. So it sounds like a stupid distinction to make, but it depends on your perspective of whether this cylindrical thing, which is nice and simple, is sort of preferred over these off-diagonal terms or not.
So you're just discussing how you go from the computation for an average of theory to computation for a single theory.
Yeah.
And if I understood correctly, we understand exactly how we would go about that on the boundary side. You just not throw away the off-diagonal.
Well, we understand only in these simple models like JT gravity. In something like n equals 4 super Yang-Mills, it's not well justified that you actually have something like these off-diagonal things. Yeah.
I thought what you were telling us is like, you understand why on average only the diagonal is important in this double sum over orbits, for example.
Yeah.
But in principle,
you should include the off-diagonals.
The off-diagonal terms, and then, depending on what question you asked, if we change the answer a lot or if we not.
Exactly. Yes.
But we don't know what the analog of including the off-diagonal terms is on the gravity side.
Only in these specific cases. In this eigenbrane case, and basically in this model that is being studied by Don Marolf and Henry Maxfield.
Oh, I see those.
There's a gravity picture, and it's sort of baby universes in random final states or initial states. It depends on your choice of time slicing.
Are you going to say anything more about that?
Just the last slide is just that. Well, that's the thing I talked about. Oh, then I'm not going to mention that. But this has basically already been said before I was born by Coleman, Giddings, and Strominger, where they studied these things, and they found that so we've opened the Pandora's box of baby universes and closed universes and stuff like that when we had these handles, because if you slice them, you're considering intermediate states of baby universes. In these calculations, I started in the Hartle-Hawking state, and I had no baby universes out there. But that might have not been the right way to set up the calculation. Why not put the baby universes in a non-trivial state? And Coleman, Giddings, and Strominger said if you put them in certain special states called alpha states, you get something which doesn't look like an average. These alpha states are like coherent states of the baby universes, basically. So if they give you a baby universe, it doesn't change the state of the baby universes. The baby universe will affect you. It won't change the state. So the baby universe state just factors off. So I think, basically, their scenario was a little bit backwards from what we want to do. They started by assuming you include all these handles and stuff like that, and they said you get this picture where you can see these alpha states come out of the calculation. But what we really want to do is take a model where we think there is no ensemble. JT gravity is not one of such models. And we want to see something like the structure emerge, but then there's something like a specific alpha state instead of an ensemble of alpha states. So somehow there should be some models that pick out a specific state of the baby universe as special. So the correction of the calculation that I was doing would be that you're supposed to put the baby universes in a non-trivial state. And somehow the UV details or whatever, something about the system picks that state out as special. And those will give these off-diagonal terms. which make the calculation not look like an average. But this is just somewhat speculation. But yeah, that's what I want to end on, I suppose.
So is there any difference between a theory where I didn't have all the alpha states to start with, and a theory which I had them to start with, and then I measure enough I do enough measurements to nail down the parameters? Is there any difference between those two scenarios?
Yeah, I would hope so. And the reason is that we think that so if you take this gravity viewpoint where it seems like there's not an issue with having an arbitrary state of the baby universes. If you think that there's no obstruction to creating all sorts of different baby universe states, then it seems like you run into the situation where you have an ensemble of dual descriptions. But we think something like n equals 4 super Yang-Mills is not part of an ensemble. So whatever is dual to n equals 4 super Yang-Mills, there should be some obstruction to varying the baby universe state. So there should be some bulk reason why you can't have this freedom to change the state. And I don't know what that is, but just a very vague hint.
I'm just not sure that you're answering the question. I think you're answering the question of whether there's a difference between ensemble theories and having just a single theory.
Mm-hmm.
That I completely agree with. I guess let me ask my question differently. I don't know how it would make sense for the real world to be described by an ensemble of theories.
Yeah.
We could just go and measure the coupling constants.
Yeah.
We can parameterize our ignorance by an ensemble of theories for a while, but then we measure which
Yeah.
is the right one and we're done. And at that point, we normally can just forget about the fact that we once didn't know.
Yeah.
And there should be no consequences to any predictions coming from that. That's why I'm puzzled by what the role of, I mean, I agree that maybe we can go from an ensemble of theories to having just a single theory operationally by measuring the coupling constants. But I don't understand how that's an argument in itself for why certain things that we calculated for the ensemble of theories should still be the right answer for the single theory. There will be some things that will be, and there will be some things that won't be.
Yeah, no, I agree. I agree. I don't think that's an argument. I don't think it's I think there's something we're missing that if for theories like n equals 4 super Yang-Mills, like maybe the real world where there's no ensemble, something we're missing in the gravity calculation that once you include it, the calculations you do look like these calculations people are talking about where you do enough measurements and you're in a fixed alpha state or something like that. The calculations look similar. You get similar answers, but there's something fundamentally different about what we're supposed to be doing. And I don't think it's an argument that
It may just not be a pure gravity calculation.
there may not be. Yeah. Oh, yeah. I would suspect there's not a pure gravity calculation, like if I just had to bet on it or something like that. Because to get the right answer, you need to know, to get the right answer for something like n equals 4 super Yang-Mills, you need to know what the actual fundamental degrees of freedom are. And it's not just visible in gravity. You need to know a little bit more than that, probably. You need to know about all the brains and whatever. Pardon me?
The miracle is how much you can already get.
Yeah, exactly. Yeah. So this picture here, maybe I'll amend this picture a little bit. I don't mean this to be here it can be very non-semi-classical. Are you happy with that? Like, I would expect that if this is the right calculation to do you actually understand the bulk theory, you find that you're supposed to sum over geometries like this. Here it can be very stringy and brainy or whatever. Semi-classically could just be very out of control. That's the sort of thing I actually imagine. This is just a very bad cartoon of that. Yeah.
So in the eigenbrain story, this is by Mertens and so on.
Yeah.
Is there some stringy degrees of freedom that live there?
No. So what they describe these states by in terms of asymptotic boundaries, and they just put some fixed energy there. And you have in JT gravity you have freedom to change all the energies. There's nothing stopping you from choosing different energies. So they on the one hand, don't have any extra degrees of freedom. It's pure JT gravity. On the other hand, they find this immense freedom to change the baby universe wave functions. So, yeah.
Okay, and is it possible to push that all the way to like get all the, like just a single theory?
What's their thing is useful for is, say you try to fix you fix a bunch of energy eigenvalues that are very, very closely spaced.
Yeah.
You say you try to fix them up to some high energy scale. You put them very, very closely spaced. Then you expect that the eigenvalues that you're averaging over are repelled from the ones that you fixed. So they're very unlikely to be in this low energy region. Then if you calculate anything that's only sensitive to low energies, like two densities and low energies, it wouldn't really know about the averaged eigenvalues. So it basically acts like up to small errors of fixed thing, but it's up to small errors.
May I just clarify something? So in the beginning you said like the physical properties of spectral statistics and stuff, like the average properties, you could get by either considering an ensemble or considering a single instance, but averaging it like
Yeah.
But now you're saying that the latter case doesn't have an interpretation gravitationally, and only the former, the ensemble one.
Yeah, that's the mystery. So like.
Is that one like a correct conclusion?
Yeah. So if I wasn't if I was considering a system that's not part of an ensemble, I'd calculate the spectral form factor. If I do this, what I thought was the good gravity calculation for it, I get a wrong answer. But I get the wrong answer for the spectral form factor, but I get the right answer for the time window average version of it. So it's like the spectral form factor is like the time window averaged one plus corrections. And those corrections, those are the things that this gravity, it's harder to get in gravity. Yeah. In terms of the energy windows, it's like if you put the,
I thought you should actually calculate the average corrections as well.
And so you can calculate the statistics of them, all the statistics of them. So yeah, it's interesting that you can calculate all the statistics. So what it says is that, what that made me feel like is this whole picture of wormholes can't be so far, like I would hope that something like a bit of a mild modification of the wormhole story would be able to account for the actual specific instance. Because say we had a calculation that was actually going to give you the right answer on the nose for a single instance. Then it's maybe some complicated thing. But that we know that if you do anything, calculate any statistics of that thing, do any sort of averaging, the calculation immediately turns into a nice simple wormhole calculation.
But that sounds like an interesting question. You could probably, we know presumably how high of a moment, up to how high of a moment you have to calculate to basically recover the exact answer, right?
Well, you can't know the exact, like you can still have an ensemble and calculate any moment you want to arbitrary accuracy, and that'll never tell you that you're in a specific instance. It's like if you take some probability distribution, you try to you can calculate any moment you want, but yeah, it's a little.
If that's the case, then I don't see.
You get like infinitely much info. So all the moments aren't. You're getting infinitely much information from infinitely many moments, but that's not enough to tell you that you're in a specific.
I would have thought that maybe for enough moments the calculation breaks down.
That's for a system that's like real, that's not part of an ensemble, probably. In JT gravity, it never breaks down. But JT gravity is dual to a genuine ensemble that's well defined and well behaved. So you might expect in something which is a little bit that's more constrained and it's not part of an ensemble, if you do the calculation correctly of all the moments, you'll find something funny happening. But in JT gravity, nothing has to go wrong. It shouldn't go wrong.
Okay, so let's make a few again.